Alright, so again, we're talking about continuity and limits. By the end of today, which is a short day, you guys are going to be able to use limits to determine the continuity of a function, okay? So we're going to be looking at a whole bunch of different functions, and we're going to determine whether or not they are indeed continuous. Now, this will be probably one of the few lessons where you will not be able to use your calculator, okay? You will not be able to use your calculator, so you won't need it today. Because there's always an algebraic way to determine a lot of these things that you guys do using your calculator, okay? So to start off, we are going to take a few notes that you guys are going to do on your lines. There is going to be a foldable that is going to go into your book, okay? It is going to be of this nature. So if you want to kind of plan for where you might glue it in, then take your notes, respectively around it, okay? I like envelope size. So, don't have to get the graph in, it's more just there for a visual, but you definitely want to get down that a continuous function has no breaks, no holes, and no gaps. Okay? No breaks, no holes, and no gaps. So in this picture, is this a continuous function? No, why not? That's an open circle. This right here in this picture that we have is an example of a hole that's in our function. In order for a function to be continuous, it can't have any holes. It can't have any breaks. It can't have any gaps in the picture. Okay? So basically, I need to be able to put my pencil down on the actual graph itself and be able to trace over the graph without having to pick my pencil up in order for it to be continuous. If I did that here, and I tried to trace over it, starting out, I'll be okay. I'll be able to trace over it. But then in order to continue my journey, I would have to pick up my pencil to jump over the hole to keep going. So I should be able to trace over a function without having to pick up my pencil to continue tracing over it. Does that make sense? Okay. Now, the concept of approaching a value but never reaching it is called a limit. All right? So when we're talking about continuous functions, we're going to be using the terminology of a limit, which basically is talking about as your x values get closer to a particular value, what's happening to the y's, okay? Along your function, as x gets closer to 2, okay? As x gets closer to 2, what's happening to the y's? What's happening to the y values? They're increasing, and they're actually getting close to a number. What number are we getting close to as we get closer to that hole? What did you say? About 7. Okay? So that's the concept of the limit, okay? It's about approaching a particular value. That's what the limit is. Okay? And we're also going to be talking about this a little bit more as we talk about continuous functions. Now, there are 3 different types of discontinuities. You have infinite, you have jump, and you have removal. Okay? You have those 3 different types of discontinuities, and the pictures that you see up here are examples of these discontinuities. Now, again, you do not have to get these pictures down. When I give you your foldable and whatever else we're cutting and gluing out today, you'll have examples of these things, okay? Not these necessarily, but examples of these things, okay? You have these 3 different types. An infinite discontinuity, that's the official word for it, okay? But the garden variety word would be a vertical asymptote, okay? So if we have a function that has a vertical asymptote in it, it's not continuous. It has an infinite discontinuity. So if we look at this first graph down here at the bottom, you see how that orange line, that discontinuity right there? It is an infinite discontinuity, which means that this function right here is not continuous. And 8 because there's an infinite discontinuity there. Does everybody understand that? Jump is jump. There's no guard right for that. It's pretty straightforward, okay? Like if you're tracing over the graph and you have to jump to get to the next one, then it's not continuous. So for example, we look up here at this top one. I'm going along the curve, okay? I stop here, but in order to get to the rest of my function, I have to literally like pop up to 4 to keep going. Everybody see that? This right here would not be an example of a whole. This right here is a jump. Okay? A removable discontinuity, the garden variety word for that is a whole. Okay? So whole, removable, they mean the same thing. Okay? This example down here has a removable discontinuity. Okay, I'm tracing along the graph. I have a hole that I have to skip over to get to the rest of the graph. Does everybody understand the difference between a jump, which is in this example, versus a hole? Or removable? Yes? Now clearly this function right here has another discontinuity. What other discontinuity does this function have? Besides infinite. It does have a jump discontinuity. Very good. Thinking about our parent functions. Think about your parent functions. Don't look back. Think about them. So just took a test. This should be out your mind already. Are all of our parent functions continuous functions? Raise your hand if you can tell me one of them that's not continuous. The square root is actually a continuous one. It is continuous one. Lisa. 1 over x, which is called the reciprocal. The reciprocal function. You guys remember what reciprocal looked like?
It's like has a vertical asymptote.
It does have vertical asymptote. It looked like that. This one, that parent function that is not continuous, it has an infinite discontinuity. The greatest integer function, that one looked like what? Like steps. It definitely isn't continuous. What type of discontinuity does it have? It has jump. Is there another one? Well, no, this actually would be the jump because we actually have to take it up to get to the next one. Were there any other ones? The one that look like this? Well, no, be careful. We can actually trace them on this one and never pick our pencil. We just come to like a turn, but we don't actually pick it up to trace over it. Were there any others? Are we good? All the other ones are continuous. Yes. What are the other ones? Absolute value. So we have that one. Square root. Yep, that's continuous. Cubic. X squared. The quadratic one. That's 1, 2, 3, 4, 5, 6. Listen to linear. And constant. Okay, yes, all of those are examples of continuous functions. Except for those two. Good stuff. All right. So how do you know if a function is continuous or not? Okay? There are ways to distinguish whether or not a function is indeed continuous. A function, f of x, is continuous at a point. At a point, f x equals c if the following 3 conditions are met. The first one, f of c is defined. F of c is defined. Now this should look familiar. We've kind of seen this notation before, haven't we? Doesn't this look familiar? Like f of x, right? But instead of an x, there's a what? C. And if you look up here at the top, it says x equals c. So that could be x equals a number, like x equals 2. So f of c would actually be f of 2. So the first condition for a function to be continuous basically says that at that x value, I need to have a y value. Because doesn't f of x mean y? So it's basically saying that I need a y value. Open it up. You should have, if you just open up the first flap, you should have this graph and then a blank right beside it, right? Look at this graph. This graph does not meet the first criteria to be continuous. It's not continuous at -1. And why is it not continuous? There's a hole there. And in order for a function to be continuous, we can't have any holes in it. Okay? So explain why the graph on the left are not continuous at the indicated point. There's a hole. Okay? You can say there's a hole. You can also say that it's not defined at x equals -1. At every other x value, it is defined, but at -1, there's that hole there. So it's not continuous at -1. It's continuous everywhere else, but not at -1. Okay? Questions? The limit as x approaches c of f of x exists. That's the second criterion for a function to be continuous. The limit as x approaches c of f of x exists. Now here's that concept of a limit. I talked about it before we went forward in the very first slide. This basically says is that as your x's get closer to a particular value, and I mean not just coming from the left-hand side, but coming from the right-hand side, it exists. In other words, it's approaching the same number. It's approaching the same number. If you want to kind of put that in parentheses, go ahead and do so. It approaches the same number from both sides. That's what number 2 means. Approaching the same number from both sides. And that's the official way to actually write it. Open it up. Look at those. Look at that next example. This one fits criterion 1. What was criterion 1? What was the? It's defined, meaning that at 2 it's defined. Do we have a y value at 2? Yes, that closed circle. Okay, so it fits criterion 1. It is defined. But if we look as x approaches that number from the left-hand side and from the right-hand side, aren't we approaching 2 different y values? What y value is it coming from the left-hand side? What y value have we approached? 1. And then over here from the left-hand side, what y value are we approaching? They're not the same. So even though it's defined at 2, they're not approaching the same y value. So that's what makes this one not continuous. Okay? So right here in this open box, I want you in your own words, so that way when you go back and look and you to study, how would you explain this? Why is it not continuous at 2? In your own words, I want you to write that down now. Number 3 is a combination basically of 1 and 2. Okay? It says the limit as x approaches c of f of x equals f of c. So it's like the right-hand side is the first criterion, and the left-hand side is the second criterion. It's just combined them. But this basically says that whatever f of c is, whatever that y value is, that should be the number that we're approaching from the left-hand side and the right-hand side. They have to equal each other. So in other words, whatever answer you got for number 1 should be the same answer you got as you're approaching from the left-hand and right-hand side. Okay? So look at this example. It passes criterions 1 and 2. Criterion 1 says f of c is defined. At 4, what is our y value? When x is 4, y is what? Look where it's defined at. It's 6. Okay? It's defined at 4. When x is 4, y is 6. And then as you approach 4 from the left-hand side and the right-hand side, what y value are we approaching? It's approaching about 1.5. About 1. But it's approaching the same number, wouldn't you say? So this is criterion 1. It passes because it is defined. It passes criterion 2 because it's approaching the same number from the left-hand and right-hand side. But it does not fit criterion 3 because these numbers are not the same. In order for it to pass criterion 3, not only does f of c have to be defined and we have to be approaching the same number, but these two numbers have to equal each other. So basically, when you're trying to figure out if a function is continuous, you'll go through the 3 steps. Check to see if it's defined. Write that number down. Look at what number your y value is getting close to when you approach it from the left-hand and right-hand side. Write that number down. and then see if those two numbers are equal to each other. If they are, then this is a continuous function. Go ahead, take a moment, write down some words, whatever you need to help you remember this criteria.